Okay, in this video, we are going to study the key ideas of concurrent data structures and one of the first implementation strategies that is lock coupling. And we are going to discuss lock coupled linked list. So, concurrent programming is fundamentally about concurrent data structures because multiple threads are trying to access the same resource, and the resource is fundamentally about data structures. And the concurrent data structure is the heart of the concurrent programming, and it is the key objectives of this course basically. And there are the three criteria for the concurrent data structures: safety, scalability, and progress. And let's look at each of them a little bit more detail. For safety, CDS needs to satisfy some specification, and one is what is called a sequential specification. It means that, if you have a concurrent queue, and it should work as if it is a sequential queue. So if two threads are pushing and popping a value to the queue, then the operations are returning the return values as if they are working on a sequential queue. So if it returns some random values, you can no longer say it is a concurrent queue. It needs to return a specific value that is governed by the queue specifications. And furthermore, you need synchronizations. If thread A pushes a value and thread B pops the same value, then there should be some release acquired synchronization between the pusher and the popper. The reason is that the queue can be used as a communication channel. It sends the value to signify something. And in order to do so, there should be some release acquired synchronization between the pusher and the popper. And the second objective is the scalability. Okay, safety is the minimum requirement for CDSs. But what the purpose of using concurrent data structure is scalability. We hope that this is much more scalable, especially for the parallel architectures than the sequential data structures. And the scalability means that it shows better performance as the number of cores grow. Ideally, it wants to achieve linear scaling. That means that if you double the number of CPU cores, then performance is also doubled. But in reality, it is very much difficult to achieve linear scaling, especially for more than 16 threads. So you need to think about the performance drop compared to the linear scaling, but still you want to make it work better. It should be sublinear scaling, but you want to drop as less performance as possible. And finally, you want to guarantee some progress about the concurrent data structures, which means that you want to somehow guarantee that your operations will be finished at least. So there are multiple notions of this progress, and lock freedom means that if multiple threads are trying to do the same thing, then you want to guarantee that at least one of them will succeed finishing its operations. If multiple threads are trying to acquire the lock, then at least one of them succeeds. That's basically what is guaranteed, what is meant by this lock freedom. And wait freedom is a little bit more stronger condition, which means that if multiple threads are trying to do the operations, then I will eventually take turn. So even though there are multiple contentions even though there are many other threads that is trying to acquire the lock. And I will eventually be able to acquire the lock. So that is the meaning of wait freedom. So spin lock is not wait free. It is lock free, but it is not wait free. But the TKN locks and CLH locks are wait free because it is guaranteed that one day I will succeed in acquire the lock. So that is basically the meaning of the lock freedom and wait freedom, the progress guarantees. And there are a way to achieve these desired properties for CDSs. So for safety, the key idea is protecting a data structure with locks or more primitive synchronizations. So one of the implementation strategy is protecting a sequential data structure with a global lock. So then you will turn a sequential data structure into a concurrent data structure that is protected by a lock. It is the easiest way to do so, and most of the implementations use this implementation strategy, but it is less scalable than the other options. Another option is protecting a data structure with more fine-grained locks. So there are multiple locks, and each lock protects a subset of the entire data structure. And by doing so, you can reduce contentions very much because multiple operations that is accessing different part of the data structure can coexist. An even more scalable approach is protecting data structure with a very custom synchronization protocols. And at the later stage of this semester, we are going to study such synchronization protocols and fine-grained concurrency and fine-grained data structures, concurrent data structures. And usually, the specification is called the linearizability, which is meaning these two, sequential specification plus synchronization. And this is usually called the linearizability. And the concept is explained here. So if you're interested, please go to this link and see what's going on there. And for the scalability, as I discussed in the previous slide, the first key idea is reducing contention by shrinking lock protection scuffs. So using multiple locks and let each lock protect a smaller subset of the data structures. By doing so, you can reduce the contentions. The second key idea is reduce cache invalidations by avoiding writes. So writes are usually detrimental to the performance because it needs to exclusively acquire the cache line, and it will invalidate all the other threads' caches. So in order to avoid that, we want to avoid writes as much as possible, and this approach is usually called optimistic concurrency control. You read something to guarantee something, but after you read something, you cannot be sure about the invariant, and you need to check again later. So if you succeeded in the later check, then you are happy. But if it is not, you need to throw away your operations, for example. So in that sense, it is optimistic. It is optimistically assumes that, for example, a value will not change for some period of time. If it is the case, you will get performance boost. And if it is not the case, then you need to fall back. So that is basically what is meant by this optimistic concurrency control that tries to reduce cache invalidations by avoiding writes. And as a case study, we are going to study optimistic lock coupling, but only after we study the lock coupling. Oh, this is a typo. This is not about homework 2. So it is for the last semester's homework, and in this semester and later, will not applies. And the last desired property of CDS is progress, which I said is the meaning of them are like this. And the key idea for achieving lock freedom is designating a single RNW instruction as commit point so that at least one CPU core will succeed each RNW, which means that, for example, in spin lock, it has a lock location, and multiple threads are trying to acquire the lock concurrently by updating the lock variable by some RMW instruction. And the hardware architecture guarantees that at least one of them will succeed in doing the RMW instruction. So by doing so, we can achieve the lock freedom. At least one of the ongoing operations is completed someday. At least one of the threads will succeed in its RMW instruction. And there is a notion of wave freedom. And the key idea for achieving wave freedom is that each thread publishes its ongoing operation so that the other threads can see its operations. So you need to guarantee that your operations will be completed someday. How to doing so? You are publishing your operations and let the others do your operations on your behalf. So usually, the lock freedom means that there is a winning thread. There is a thread that wins the race and succeed in the RMW instruction. So the winner is going to take in charge of doing the other thread's operations. That is meant by this wave freedom. So that is the key idea of this achieving the wave freedom. So for example, this YMCQ is a primary example of a wave-free queue, which we are not going to study in this semester because it is much more complicated than the other data structures. But if you're interested, please read this paper. Also, this is a very fine paper that is describing or defining the meanings of this lock freedom, wave freedom, and other kinds of progress guarantees. And it classifies the many guarantees into some criteria. So it is very fun paper. So if you're interested in these progress guarantees, please go read this paper. But we are going to study only lock freedom in this semester because the other progress guarantees are difficult to achieve and difficult to study. We are sticking to lock freedom in this semester. Okay, as the first example of data structures, concurrent data structures, we are going to study lock coupling. So here is a lock coupled linked list. And this is just a singly linked list. And the only difference from the sequential linked list is that each node has a lock. And the lock should be held when accessing its next pointer. So each node has a lock and the next pointer, and the lock should be held to access the next pointer. So, or you can say that this lock is protecting this next pointer. And you need to guarantee that you should acquire the next node lock before releasing current. So if you want to traverse this linked list, you need to acquire the locks, and before releasing a lock here, you need to acquire the next node's the lock. So here is an example. So you can traverse this linked list by first reading the head pointer. And at this point of time, you don't need to protect the lock because head is shared and head is immutable. And you acquire a lock for the next pointer before you read the next pointer. And because this next pointer is protected by this node's lock. That's the reason why you need to acquire the lock before reading the next pointer here. And you need to acquire the next node's lock. And only after that you can unlock the previous node's lock function. Previous node's lock. So the reason is that you want to make sure that this current node is not detached before you access it. So in order to do so, if you acquire this lock after this is unlocked, it may be the case that at some point of time you hold no locks on the linked list. So you know nothing about this linked list. Maybe it can be possible that this node can be detached and deallocated by another thread. You need to avoid such a situation by at least you're going to hold at least one node's lock. So by doing so, you are guaranteed that your traversal is not detached. Your traversal is not going to be deallocated. So let's see this again. You lock this, and you read this. And as far as this lock is held, you are guaranteed that this node will not be deallocated. After that, you acquire the next node's lock, and it is guaranteed that this node and this node will not be deallocated. You know that they exist. After unlocking this lock, then you no longer know whether this will be deallocated or not, and at least you know that this will not be deallocated. You know it exists just. And you can do the remaining traversal by reading and locking, again. Crucially, as I said before, you have to acquire this lock before you unlock the previous node's lock. So that is to make sure the current node is not deallocated. Okay, so far so good. So the reason why it is called lock coupling is that there is a couple of locks always. You acquire a couple of locks and you unlock one of them, and you lock on one another, and then you unlock this, and again and again and again. So that is the reason why it is usually called hand-over-hand locking. You lock it, you lock next one, and hand is over now. Then you unlock the previous lock, and then you lock the next one, and again like this. So this is as if the locks are held hand over hand. So that's the reason why this is lock coupling and hand over hand at the same time. Okay, so here is how to implement the linked list operations for these lock coupled data structures. So if you want to insert B between A and C, you first acquire a lock and read the A's next pointer and allocate B with its next pointer pointing to the C, and then write A next to B. So at any point, you can see that. So you're going to change this pointer here, right? So that's the reason why you need to hold its lock always from the beginning, because you're going to change this pointer. So after traversing this pointer, you need to acquire the lock, and after traversing, you create a new node, and you should still hold the lock because you are going to change the next pointer. The next pointer should be changed under the lock is held. And now suppose we want to remove B. B is this pointer between A and C. And what we should do is this. You acquire A's log, read A the next, that is B, and acquire B's log. And now you want to remove this node. And you want to change this pointer here. So you're not going to release A's log because you're going to change this pointer. So you need to protect this pointer using this lock. So instead of unlocking A's lock, you read the pointer again. And now you write A next to C. Because it is safe, because you are holding the lock for this A. And now you release B's lock and then free B. So you can do that because you are the only one who can hold the pointer to here, because no one can point to the other threads can point to this block, because in order to do so, it must have already acquired this lock, but this lock is held by me. So no one is going to access this. So that's the reason why we are free to free this block B. So this is basically the linked list operations. So insertion and removal, they all are involved with locks like this. So there are pros and cons of lock coupling. And the first pros is that it is a relatively easy implementation strategy. It is much more easy than the fine-grained concurrent data structures. And yet it is quite scalable. For example, for the linked list, they are concurrently holding only 2 locks in the data structure. So it may be possible that multiple threads are accessing the linked list at the same time by accessing different part of the linked list structure. And the cons is that you acquire the locks even for reads, even for travel, so you need to acquire the lock. So there is a cache invalidation due to writes. And this lock acquisition inspired writes will incur cache invalidation, which may degrade the performance. And also, you need to take into account the possibility of deadlock. So this implementation doesn't have deadlock because the locks are ordered. So and there's no way locks are no way to enter deadlock. But you need to take care about this. You need to take care about the lock order so that you can avoid the deadlock altogether. So that's one of the cons. And the alternative will be lock-free concurrent data structures. So here, it is very lockful. We protect nodes with locks. On the other end, we can think of lock-free data structures, which doesn't have locks. But the cons is that it is much more difficult than lock coupling. But the process, it is much more scalable, and there is no cache invalidation due to lock acquisition or no deadlock, etc. So in the remaining of this semester, we are going to study these lock-free data structures and their properties and their memory allocator and deallocator.